By this point in the course, you should be at a point where you have sufficient knowledge to configure the M1 ECU to run your particular engine. You should also be able to properly tune the fuel delivery and ignition timing correctly, as well as many of the more advanced aspects that the M1 can support. This does leave one area we haven't touched on yet, which is transient fuel enrichment, often referred to as acceleration enrichment. Traditionally, this is dealt with using an additional fuel delivery that is relative to the rate of change of throttle position. While this is effective to a point, it doesn't properly deal with what is actually going on in the engine and why the engine needs transient enrichment in the first place. With the M1, Motec have moved to a different way of controlling and transient enrichment that more accurately describes what's happening inside the engine. This is known as fuel fill modelling, and to understand how to tune it, we first of all need to understand the principle behind it. Let's start with a simple analogy. First, let's take a normal kitchen chopping board and hold it on a 45-degree angle into a sink. Now we can take a spray bottle filled with water and spray it against the chopping board. If we spray repeatedly, we'd see that for the first 2 or 3 sprays, no water drips off the chopping board. Instead, the water is forming a surface film on the chopping board. If we keep spraying though, eventually the pool gets large enough that the water will start dripping off the end of the chopping board and into the sink. From this point on, each time we spray the board, water will immediately drip off it. This is similar to what's happening inside the engine, with the injectors spraying fuel against the manifold wall. Under steady state operation, a portion of the fuel delivered by the injector will form a puddle or film of fuel on the intake port wall. The size of this fuel film will be affected by numerous aspects such as injector placement, wall temperature, air pressure, airspeed, and injection volume. The fuel film will build up to a certain level and then will begin to evaporate off. Some of the fuel from the film may also end up entering the cylinder in the form of liquid droplets. Under steady state conditions, this fuel film is topped up by the injector at the same rate it evaporates, so the volume of the fuel film stays constant. As I've mentioned, the volume of the fuel film depends on many parameters. Some of them, such as the injector placement and spray pattern, don't tend to change much and remain constant. Others, such as port temperature and air temperature, tend to change quite slowly and again don't have a considerable impact on the running of the engine. Airspeed and air pressure, however, can change very rapidly, and these can have a large influence over the volume of the fuel film. This can cause a lean mixture we see when rapid changes in throttle position occur. Let's see why this is the case. The biggest influence over the volume of the fuel film is manifold pressure, and this is affected dramatically by changes in throttle position. Under low manifold pressure, the volume of the fuel film will be lower, and under high manifold pressure, the volume of the fuel film will increase. The volume of the fuel film tends to take some time to build up though, so when the manifold pressure moves quickly from low to high, there will be a period of time, usually in the order of a few tenths of a second, during which the fuel film volume increases. During this time, a portion of the fuel injection pulse is being used to increase the volume of the fuel film and hence isn't making it into the engine. Once steady state conditions are again established at the new manifold pressure, the volume of the fuel film will have stabilised and the fuel delivery to the engine is again correct. It's during these periods when the fuel film volume is increasing or decreasing that the fuel delivery reaching the engine cylinder will be incorrect. Let's look at an example where the engine has been tuned correctly in steady state conditions at 2000 RPM at 2 points in the efficiency table, 40 and 80 kPa. In both sites, the efficiency table has been correctly calibrated to achieve a lambda value of 0.90. At 40 kPa, this requires an injector pulse width of 3 milliseconds, and at 80 kPa, it requires a pulse width of 6 milliseconds. Let's assume, however, that at 40 kPa, 2.5 milliseconds of the injector pulse width is making it directly into the cylinder, and the other 0.5 is topping up the fuel film. Of course, the film is evaporating at the same rate it's being topped up, so the cylinder is still receiving the required 3 milliseconds of fuel delivery. At 80 kPa, 4.5 milliseconds of the injector pulse width is delivered directly to the cylinder, and 1.5 milliseconds tops up the fuel film. The fuel film in this case is grown by the equivalent of 1 millisecond. Again, under steady state conditions this doesn't matter, as the fuel evaporates off the fuel film at the same rate it's topped up. The problem occurs though when the throttle is snapped open rapidly and the manifold pressure moves from 40 kPa to 80 kPa. In this instance, 1 millisecond of the delivered fuel pulse width will go to increasing the size of the fuel film. The engine will therefore run lean momentarily while the fuel film builds up and reaches equilibrium again. Now we have a proper explanation of the fuel film, we can look at how to adjust it in the M1. Properly configuring the fuel film model does require the engine efficiency table to properly and accurately be calibrated first, otherwise you'll be trying to use the fuel film settings to make up for inaccuracies in the efficiency table.